Now what we want to do is talk about tension. So here's a situation. We have a rope pulling up on a safe, right? And so like we would say, what kind of force does a rope exert on the safe? And we would say tension, right? But what exactly is tension? I mean, what is it? So what we want to do is we want to just look at this segment of the rope, right? Look at that segment of the rope. So you can see that the top part of the rope pulls up, the bottom part of the rope pulls down, right? And so obviously this here does not accelerate, right? Because this up, this down, say magnitude, okay? So that doesn't accelerate. But like what's getting pulled? What's going on? Like if you had a super good microscope, what would you see in here? What would you see in there? So this is what you see, right? Remember, a rope is made out of molecules. Molecules are held together with molecular bonds. We model the bonds as springs. So here's the stretched molecular bonds, right? And so here's this force pulling down on them. Here's that force pulling up on them. Now, if these forces are greater than the strength of the bonds, the rope breaks, but we don't want to talk about that, okay? All I'm saying is that it's the molecular bonds that are getting stretched, okay? So here's another way of it, right? So there's the upward pull from the bonds above, or the springs above. There's a downward pull from the bonds or the springs below. That's really what's going on with tension. All right, now I'm going to ask you some questions, and most students find these challenging. So make sure you're totally awake and paying attention. Okay, so here we have a student. All right, so the rope is attached to the wall. That's important. And the student is pulling to the left with 100 Newton force. Okay, what is the tension in a rope which is attached to a wall and pulled by a student with 100 Newton force? So pause your video and figure it out. Okay, the student's pulling on it with 100 newtons. So what's the tension? Well, 100 newtons, right? Again, I think I would do it like this. Just consider this section of rope right here. The student's pulling on it 100, and then there's 100 going that way, right? You can say the wall is pulling over 100 that way. So this section of rope doesn't accelerate. So the tension's 100, right? Tension's 100. Okay? Tension's 100. All right? Oh, yes. Oh, yes. Okay. So here we have two people pulling, each with the same force, 100 newtons. The rope doesn't accelerate, right? It's like a tug of war and nobody's winning, So what is the tension in a rope which is pulled by two students, each with a force of 100 newtons? Look at that. Think about it. Look at that. Think about it. Don't philosophize. Analyze. Look at that. Think about it. What's holding the rope? The wall. What's holding the... So what's different about this than this? Here the rope, the wall is holding it. Here the female student is holding it. So what's the answer? So pause your video and think about it. Pause your video and get ready to vote. It's 100. Okay, it's exactly the same as that one. There the wall is holding it. Here the female student is holding it. Same thing, exactly the same. Let's see. Yeah, student number 2 is equivalent to the wall in the previous question. What is the reading on the spring force scale? So we have a massless string, we have a massless and frictionless pulley, right? So this thing is the spring force scale, right? So what's the reading going to be? So pause your video and figure it out. Well, it's a force scale, right? So what's the force? The force is the weight of the block, which is mg, which is 5 kilograms times 9.8 meters per second squared. And guess what that is? 49 newtons. Okay? All right, how about this one? Okay, now notice what's holding this? The wall, right? Okay, so what is the reading on the spring force scale? Assume massless strings and massless frictionless pulleys. So pause your video, figure it out. Again, compare that with that. Okay, ready? Let's vote. So here, the wall is holding this string. And here, this thing is holding the string. But come on, it's the same thing. So it's 49 newtons. Now, every time I teach this, there's always some people that just don't believe it, which is fine. I mean, physics is an experimental science, right? So if you don't believe something, you just do the experiment. So that's what we're going to do. We're going to do the experiment. Okay, so you actually have to be able to look at that and me. All right, so let me explain what I have here. So this is a cart. On top of the cart is a force sensor, right? So right here. So this thing, you know, I mean, we're pulling on it, and so it measures the force on it, okay? Right here, this thing, okay? And then I have it connected to some stuff. And what we're going to do is we're going to measure the force. So we're going to measure the force that this force sensor measures, okay? What I'm going to do, first I'm going to do it like this. So that's kind of like, you know, when the string was attached to the wall, right? So first I'm going to do that. And then I'm going to do that, okay? So basically, oh, come on now. Okay, so first I'm going to do that. And then I'm going to do that. And we're going to see if we get the same reading. Okay, hold on, I got to switch cables again. All right, so I think this thing takes data like every, I don't know, every 1/10 of a second or every, I don't know, whatever. So you're going to see, you know, it's just going to keep on having different values of the force. And they're all going to be very, very similar, right? Okay, so here we go. So there's the first one. I got to tear the, okay. All right. So I'm holding this, and I got to tell this thing to go. All right. So what do you see? And it's minus because it's being pulled. That's the way this thing works. So, you know, like minus 0.5, minus 0.49, minus 0.51, you know, they're all like minus 0.5, right? Okay. Now I'm going to just put this over here. Come on. Okay, I'm going to just put that over there. I'm going to let go. What do you notice? Did anything change? No! Nothing changed, right? Nothing changed. All right, wherever you want to put it. It's all the same, okay? So I didn't lie, all right? So it works. All right, so you want to remember this. This is kind of a big deal, and we're going to talk about it again, all right? So, okay, so that is equivalent to that, all right? Here the wall is holding the string. Here this thing is holding the string. So most people kind of have a hard time with that one. All right. Okay, let's go. There you go. All right. Up to this point, we've always assumed that we have massless string. And I explained that a long time ago. I said we don't have massless string, but we say that the mass of the string is much, much less than the mass of the objects involved, so we can ignore it, right? That's really basically what we mean, right? Well, now we're going to say forget it. Now we're not going to say we have a massless string anymore. Now we're going to say we have a massive string, okay? So we're going to say that this string has mass ms, okay? Yeah, so what we want to do is measure the tension at this point. Now look, if this is a massless string, you know, we always say that this tension equals that tension, right? We don't even worry about it. But now, again, we're going to see that this tension here is different than this tension here. And it kind of makes sense. I mean, think about it. This tension here is pulling the block as well as the massive string, right? This tension here is only pulling the block. So we should expect the tensions to be different. Of course, if this is massless, which is what we usually assume, the tensions are the same, right? Okay, so let's work this out. This is kind of a cool problem. All right, what are the objects? We have two objects now, right? We have the string and the block. So what we want to do, you know, two objects, two force diagrams, right? Now look, all we care about is what's going on horizontally. So there's really no reason. I mean, it's frictionless, right? So we don't have to worry about the normal and the weight, because all we care about is the horizontal motion, horizontal forces, okay? All right, so let's do it. Let's do the block. So here's a force diagram for the block. Okay, what's the only horizontal force acting on the block? Well, T2, right? T2. T2. And again, I don't care about the normal and weight. I don't care about that. All right? Now let's do the string. Whatever. Okay. What are the horizontal forces acting on the string? Well, T1 is pulling it this way. Is there anything pulling it this way? Well, yeah, T2, right? I mean, right? Okay, so T2 is pulling it that way. All right. Awesome. So, you know, we use Newton's third law here, right? I'm just being lazy. I didn't write it. You know, what we really said is the force string on block equals the force block on string, which is T2. Just magnitudes, right? Just magnitudes, okay? Right? Agree? String on block, block on string, T2. So we used Newton's third law, right? Newton's third law. Okay, now, so this is kind of how you approach these kinds of problems. What is the same with this object and this object? As they move along, what's the same? What's common? The acceleration, right? They both have, because, you know, they move as a unit, right? So they both have the same acceleration, right? So same acceleration. And you're going to see that in some of the problems that you'll do for homework and exams. All right, so let's use Newton's third law, Newton's second law, right? So the sum of the forces equals T2, that equals m block A. I don't have to subscript the A because it's the same, right? Okay, so therefore, I have A equals T2 over m block. For the string, the sum of the forces, T1 minus T2, right? And that equals the mass of the string times A. Again, A is A, no subscript necessary. So therefore, the A is equal to T1 minus T2 over M string. All right, now I've got to do some algebra, and I don't have enough room. Oh, maybe I do. Okay, so I want to get at look at, it says, how does T1 compare to T2? So I want to get T1 divided by T2, okay? I want to get T1 divided by T2. Well, how am I going to do that? Well, you know, well, let's see. Let's just do it, all right? So, okay, I'm going to get rid of that. All right, so here we go. So we know that's equal to that. Let's just put them equal. So we have T2 over M block equals T1 minus T2 over M string. Now, I want to get T1 divided by T2. So it kind of makes sense that I want to get to T2 down here, right? All right. So I'm going to divide both sides by T2, then I'm going to multiply both sides by MS. Right? So I divide by T2, and then multiply by MS. Sorry. Okay? So I have MS, mass of the string, over the mass of the block equals T1 minus T2 over, 2, silly rabbit, over T2. All right, now what is this? Well, that's the same as T1 over T2 minus T2 over T2, right? Of course, that's just 1. That's just 1. All right, so now I want to get T1 over T2, so I put that 1 on the other side. So I end up with T1 over T2 equals 1 plus M string over M block. Okay, that's what I get. Now again, look. So T1 is not equal to T2 if this string has mass. If the string does not have mass, then this is 0, and T1 does equal to T2, okay? So that's why for most of the problems I guess for all the problems we've done so far until this, we've always said massless string, so the tensions have always been the same, right? But as soon as we get that string having mass, the tensions are different, okay? The tensions are different. So that's a nice problem. Make sure you understand it, especially this business here, that the accelerations are if we didn't have the accelerations are the same, we couldn't solve the problem, right? I mean, we wouldn't know what to do. So that's nice that the accelerations are the same. And you'll see that a lot. Okay, so I'm just going to do a bunch of problems for a while. Well, let's see how long, I don't know. Okay, let's do another problem. This is a nice one. This is a really nice one. Okay, M1, mass M1 on a frictionless table, thank goodness, is connected by a string through a hole in the table to a hanging mass M2. With what speed must M1 rotate in a circle of radius r if M2 is to remain hanging at rest? Oh boy! All right, now let's just think about it. What would happen if M1 were not moving at all? Well, they'd fall and M2 would fall, right? Okay, so obviously, if M1 is moving, maybe there's some particular speed where M2 doesn't move, right? So what are we saying? So we're saying M1 is moving in a circle at the right speed, so M2 doesn't move. Doesn't that kind of sound like orbital motion, free fall? Okay, good review problem, right? All right, so M1 is going in a circle. So that means it has centripetal forces, centripetal acceleration, right? Okay, so what is the what is the centripetal force acting on M1? In other words, why does M1 go in a circle? Why doesn't it just go straight? What's the force acting on M1 to cause it to go in a circle? It's the tension, right? It's the tension in a string. Okay, if this hole is smooth, which we're assuming because we don't have any choice, right? If this hole is smooth, what does the hole act like? Like a pulley, right? Like a pulley, okay? So, if we have, now they don't tell us, but again, you just have to assume it because we don't know what else to do. So we're going to assume that the mass of the string is negligible compared to these two masses. We're going to assume that the hole or the pulley is frictionless, okay? So therefore, how does the magnitude of this tension compare to the magnitude of that tension? It's the same. Isn't that great? It's the same. All right? All right, let's do it. Okay, so what are the objects? M1 and M2. So, like always, right, we have two objects, so we're going to have two force diagrams. So let's do it, okay? Now, let's do M2 first. I don't know why, but whatever. Okay, M2, equilibrium or not equilibrium? Well, it's at rest, so it's not accelerated, so it's equilibrium, right? So M2, so what are the forces acting on M2? Well, you know, gravity, M2G, and then what's pulling it up? The tension. Well, that's not so bad, right? And then M1, okay, what are the forces acting on M1? Well, you know, gravity, right? Gravity. So there's M1G. Now there's a normal force too, right? There's also a normal one. So there's N1 or N, whatever. Now look at it, it's going in a circle, right? And so let's say that this is the center of the circle. So wouldn't you agree that this is the tension, right? It's the tension that points towards the center of the circle that makes it go in a circle, okay? So that's the center of the circle. So that's where the tension points. Okay, now, because of Newton's third law, and because we have massless and frictionless pulleys and strings and all that, we know that these tensions are the same. If we didn't have that, we couldn't solve the problem. Okay, so we got to find the speed, right? We got to find the speed. Okay, so how are we going to do that? Well, this is moving in a circle, right? So we know how to do that. All right, so let's start here. So we're going to get a speed, right? So the sum of the radial forces acting on M1 is M1v squared over r. You better remember that because we just use it a lot, right? And again, that's the thing, you know, you just write it down, all right? That's always going to be true, you know, it's always true. But, okay, it's true, but we have to identify the radial forces. So number one, how many radial forces are acting on M1? Just one. And what is it? Tension. All right? So again, in the green is always true. What we have to do is identify the radial forces, and that's the T. All right? Awesome. All right, so there's our V, right? There's our V. Okay, so we're kind of getting excited, right? Okay. All right, let's do M2. M2 is at rest. So the sum of the y forces equals 0, which is T minus mg. Therefore, T equals mg. Again, you know, I hope you're at the point now where you just realize that this is at rest. So you could have just immediately said T equals mg, right? Could have immediately gone to that step, but whatever. Okay, so now, all right, so here we have the T equals mg. Here we have the T equals mv squared over r. Now we're going to put them equal, right? So now we're going to say that mg equals, oh, see, I always do this. Bad news. Don't forget your subscripts. Golly, don't forget your subscripts. All right, so m2g, equals m1v squared over r. And then we want to solve for the v. So we multiply by r, divide by m1. So we have m2 gr over m1. That equals v squared. So then we take the square root. And there you go. All right? Now, let's see if it makes sense. It's also a good idea. See if it seems reasonable. If M2 is really, really massive, you would expect that M1 has to go really, really fast, right? Well, let's see. Yeah. So if M2 is really, really big, since it's in the numerator, V would have to be really, really big, right? Right? Okay. And if M1 is really, really big, well, that's going to cause the velocity to be smaller. All I'm saying is that this thing makes sense. All right, the thing makes sense. Okay, let's see. That was that. Let's do number 5. Oh, yeah. Oh, all right, whatever. I just did that. Forget it. All right. Oh, yeah, this is a nice little review here. And there's something new I didn't tell you yet. So oftentimes you'll be asked a question, which forces form members of the same force pair? So this will help you. So forces always come in pairs, right? If there's an A on B, there has to be a B on A. Same magnitude, opposite direction. Forces in a force pair never, never, never act on the same object. And here's something new I forgot to tell you. Forces in a force pair are always the same type of force. So like, for example, Earth on me on Earth, those are gravitational forces, right? So forces in a force pair are the same type. Both gravitational, both, magnetic, both electric, both normal, whatever, the same type of force. So these 5 facts will help you figure out what are members of the same force pair. Okay, this is I like this question. All right, so there's 2 questions. There's the easy one, and then there's the harder one. Okay, so here you have a frictionless surface. You have a hand pushing on A, and A pushes on B. Mass of B is greater than mass of A, and they accelerate. Okay, you ought to be able to do this without any thinking hardly at all. All right, so identify the 2 force pairs. So pause your video and figure out the 2 force pairs. Okay, so no thinking at all, right? A on H, H on A. There's one of them. A on B, B on A. That's the other one. Okay, A on H, A on B, wrong. B on H, A on H, wrong, right? Just this, A on H, H on A. A on B, B on A. So it's the first 2. Isn't that great? Okay, now you're going to use that on the next one. Okay, identify the correct statement, magnitudes only. Now this is totally an awesome question. And I gave you so basically look at, which force is greater or equal or whatnot. So here's, in my opinion, the best way to do it. Draw horizontal force diagrams for each of the 3 objects, hand, A, and B. So we don't care about the normal and the weight, right? All we care about is, horizontal. So draw horizontal force diagrams for each of the 3 objects and compare the forces. And you don't need to do any algebra. Nothing. All right? No algebra is required. Just F equals ma. So just humor me, please, and draw the 3 force diagrams and use what we learned what you figured out on the previous question and figure it out. So please do this. So pause your video and do it. Okay, let's talk about it. All right, so hand. What's the only force acting on the hand? A, right? A, this way. So it's a force A on hand, right? All right. A. What are the forces acting on A? Well, the hand is pushing it this way. So we have the force hand on A, and B is pushing it that way, right? So we have, and remember, when I draw the lengths of the forces, I'm not trying to imply that they're equal, I just draw the arrow. So here we have the force B on A. Now notice, the hand is the object. I have hand there. A is the object, A, right? Okay, then let's do B. What are the forces acting on B? Well, just A, right? So here we have the force A on B. All right, now, it says it's accelerated, right? So there's an acceleration this way. Well, if there's an acceleration this way, doesn't this force, remember magnitudes, doesn't this force have to be greater than that force, magnitude, if it's accelerating that way? Yeah, right? So magnitude, H on A, has to be greater than the force B on A. Magnitude. So what's the answer? Yeah, right there. Okay, now notice it says here, it says A on B. Well, whatever, because remember, just magnitudes. B on A is the same thing as A on B, magnitude, right? There you go. All right, so here's how they, this is not me, okay? So here is A on H. And notice, there's the force pair, H on A. And then here, A on B, and there's a force pair, B on A. And again, if this is accelerating, this magnitude has to be greater than that magnitude. So A on H equals H on A magnitude. That has to be greater than this, B on A, which magnitude equals A on B. Ta-da! So that's a cool question. No calculations whatsoever, no algebra. Good concept, though. So that's a good test question, huh? All right, that's a good time to quit. Let's quit.